Hello, I now want to talk briefly about two of the most common types of input-output linear time invariant system that we're likely to come across. And these are systems described by linear ordinary differential equations, or ODEs for short, or systems described by delays. And so what we're really interested in understanding today is what the transfer functions of these types of system look like, and then this sort of gives you a modeling framework to build up really very complicated models. So just by combining ODE models and delay models, you can build up simple linear models for even incredibly complicated processes. So this is sort of, it's not quite as general as the full class of transfer functions, but it's sort of like a subclass that will get you very far. And we're just interested in understanding what the transfer functions for these types of system look like, and maybe see if there's any other sneakily hidden assumptions or anything like that. So we're going to start with ordinary differential equation input-output systems. So what do these look like? Well, a system of ordinary differential equations is just some linear combination of variables and their higher order derivatives. And in this input-output setting, you will typically restrict yourself to just your input and output variables and their derivatives. So our system of ODEs will look something like this. We might have y double dot, so this is the second derivative of y with respect to time, plus maybe a1 y dot plus a2 y, and this is equal to, and then we have some set of derivatives of u. So maybe we have a b0 u dot plus b1u. And so a sort of a system of ordinary differential equations looks something like this. And when we're talking about input-output systems, the variables in this differential equation are the variables corresponding to our inputs and outputs. There's no reason that we stopped at second order here and first order here. We could have gone up to whatever order we wanted. So we could have y a millionth dot if we wanted. So this is a system of ordinary differential equations, and there's another sort of essentially equivalent way to describe systems of equations like these, and that's through state space models. And we're going to talk a lot about state space models in the second half of the course, but we may as well sort of introduce them now. And a state space model is a pair of equations on the following form. It's x dot is equal to ax plus bu, and also y is equal to cx plus du. So rather than having a single equation, we in fact have two, and rather than having derivatives of y and u, we combine all of our derivatives into a single variable, which is called the state. It's a vector of variables, so this thing x, this is a vector containing a bunch of variables, say x1 and so on, up to xn. These are all functions of time. And captured within this state is all of the information about the derivatives that you would get in a normal system of ODEs. And then everything else in here are just constant matrices. So A is always a square matrix. If this vector has n elements, A is an n by n matrix. And if we're dealing with single input, single output systems, which is really what we're looking at in this course, then B is a column vector of height n, C is a row vector of width n, and D is just a number, and it's quite often 0. So this is sort of an equivalent notation for a system of ordinary differential equations that's got a bunch of advantages that we'll get into later into the course, but might as well introduce them now. So these are ODE models in the time domain, and what about delays? Well, in this sort of input-output framework, we say a delay. What a delay does is it sets the value of the output at time t equal to the value of the input, but some capital T time units into the past. So y is exactly equal to u, but it's just delayed by a length of time, capital T. And by combining these types of models and maybe wrapping around things in feedback, you can get a sort of an extremely rich modeling class, which sort of covers all of the convolution systems that we're likely to need. So what do the transfer functions for these models look like? That's what we really want to talk about today. Well, we could do the delay first. Delay is the easiest one. And in fact, I'm just going to leave this as an exercise for you to do, maybe, if you're interested. And so just by taking Laplace transforms here and using a simple change of variables, show that this equation can be written as, after taking Laplace transforms, can be written as y of s is equal to e to the minus st u of s. So this e to the minus st, this is the transfer function of the delay, and it plays the role of this g in the input-output system there. So that's what the transfer functions of delays look like. And now let's just talk a little bit more about ordinary differential equations. So how are we going to turn this equation or this equation into an input-output system involving only u and y? And here we've got, well, we have u and y, but we also got a bunch of higher order derivatives. And here we've got this sort of intermediate variable x, our state variable. And we've got an x dot, and how are we going to deal with these derivatives? Well, we're just going to show how to relate the derivatives of a variable, the Laplace transform of the derivatives of a variable, to the base variable itself. So we're really going to look at the Laplace transform of d by dt of some variable and try and see what that looks like. So we're interested in finding the Laplace transform of d by dt of some variable. Let's just go for y. And let's just try and relate this to the Laplace transform of y. So what's the definition of this thing? This is just equal to the integral from 0 to infinity of dy by dt e to the minus st dt. And sort of what's an easy trick that we could use to maybe turn this integral into something that looks like the definition of the Laplace transform of y, and hopefully it's screaming out at you. It's this integration by parts rule. So just a quick reminder, what is integration by parts? Well, I'm sure you've all seen it before. It tells you that the integral of u dot v, you seem to often use u and v. So u and v here are just two variables. This integral is equal to the product of u and v evaluated at the limits of the integral, and from this we subtract the integral of v dot u. And so what should we use as u and v in this expression? Well, it looks like we should set v is equal to e to the minus st, and maybe I can label that on. So we're going to use this for v and this for u dot. So applying this integration by parts rule, we see that this integral here is equal to, well, if u dot is dy dt, then u is just y, and then v is e to the minus st, and this is evaluated at the limits of our integral, and from this we subtract the integral from 0 to infinity of y, and then v dot, we have to differentiate this with respect to time, and we get minus s e to the minus st dt. Okay, so we're almost there. We just need to simplify this down a little bit. So how do we deal with this first bit? Well, again, we need to remember what we learned about regions of convergence for Laplace transforms, and then we see that as long as s is far enough in the right half plane, when t tends to infinity, this term here is going to converge to 0. So this is going to be 0, and then when we evaluate this at 0, we get y at time t is equal to 0, and this thing is just equal to 1. So this term here evaluates to minus y of 0, so the value of our function y at the time t is equal to 0. And here we've got two minus signs. This s is just a constant with respect to this integral, so we can pull it out. And then what we're left with is just the definition of the Laplace transform of y. So here we have plus s multiplied by the definition of the Laplace transform of y. And this here, so if I just write this down, this is our trick for relating the Laplace transforms of derivatives of variables to the Laplace transform of the variable itself. You just multiply by s and you subtract off this initial condition. And we can actually use this recursively to find higher order derivatives, and just to sort of show you how to do that. So this implies that the Laplace transform, and suppose we want to find y double dot, well, what's that? That's just d by dt of y dot. And then applying this rule here, well, this is just equal to minus y dot of 0, so the value of the first derivative of y with respect to time at the time t is equal to 0, plus s times the Laplace transform of y dot. And then just by substituting this in here, we can relate this, and we just end up with something that depends on the Laplace transform of y and the value of y and some of its higher order derivatives at the time t is equal to 0. And just by recursively doing this, we could find the Laplace transform of y double dot, y triple dot, whatever we like. And the sort of the basic pattern that emerges from all of this is that if you have a first derivative, you have an s to the power of 1. If you have a second derivative, you'll get an s to the power of 2, and so on, multiplying the Laplace transform of y. And then you get a summation involving all of the initial conditions, some of which will also have an s there. So you get this sort of bit that depends on the initial conditions, and then s to the n multiplied by the Laplace transform of y. And so just by using this, we could convert an equation like this into sort of into the S domain. So how are we going to relate this to a transfer function here, and what is going to go wrong? So you can sort of see the thing that really messes things up here is the introduction of all of these initial conditions, so the values of the variables at time t is equal to 0. And in fact, when we're talking about input-output systems, we're often tacitly assuming that these initial conditions are equal to 0, and this condition is known as, or you say that the system is initially at rest, and then you're interested in the effect of the inputs and outputs on its behaviors. So we'll talk about that in a little bit more detail in just a second, but hopefully that you can see that if we assume 0 initial conditions, then this equation here will collapse down to s squared multiplied by y, so let's put our y there here, and then here we'd have a plus a1s plus a2, and then we get the same thing involving u's, and so here we'd have b0 s plus b1 u, and then we're almost there. We just have to take this bit here and divide it through, so we could remove that and put this here, and we have s squared plus a1 s plus a2. And so this here, this is our transfer function, and it shows us how to map the input to the output y. And we can see that we could do that sort of no matter what ODE we were given. So that's okay. That's kind of, it feels like a bit of a cheat though, doesn't it? This, we'll just assume all our initial conditions are 0. It feels like a bit of a cheat, and it also, it doesn't sit very well with what we showed before when we sort of said, oh, if you have any system that takes inputs and gives you outputs, and you assume that it's linear, time invariant, and causal, then you must get a convolution system. And then straight away, when we just try and do kind of arguably almost the simplest example of an ODE, we're already running into trouble and having to seemingly make additional assumptions. So have we done something wrong here? Well, we sort of pointed out maybe a subtle piece of fine print in those, when we were talking about convolution systems, when just by saying that we assumed that the system, the output of the system only depended on the inputs, we were tacitly ruling out the effect that the output might also depend on some initial conditions. So under the assumption there's no initial conditions, there's nothing wrong with what we were saying about convolution systems before. But what we omitted to say was that maybe there's some other stuff that the output also depends on. And we see when we look at differential equation systems that, yeah, that seems to be the case. Things do also seem to depend on the initial conditions. But all is not lost. We can, in fact, incorporate any initial conditions we might have, just in terms of additional inputs, and everything will still end up being described in this language of convolution systems, or this language of transfer functions. We just can't necessarily do it quite so compactly. And I just want to draw like a little picture to show how to do this for the state space model. So we've sort of taken Laplace transforms here. Now let's take Laplace transforms of this and draw some picture and try and also build in the initial conditions. So how are we going to do that? We're sort of running out. I've left a little bit of space here. Let's try to make use of that. First of all, let's just Laplace transform these equations. So yeah, we've got vectors and matrices and things, but nothing really changes what we do here. What does it mean to Laplace transform a vector variable? It just means we Laplace transform every entry. And yeah, so it turns out if you Laplace transform every entry in these equations, what do you get? Well, you find that S multiplied by the Laplace transform of x minus x0, so this is just like our differentiation rule here, but applied to the variable x, is equal to ax plus bu, and then similarly this equation, there's no derivatives. Laplace transforming, we just turn the time domain variables into their frequency domain counterparts. Should make these look more like capital letters maybe. And then here we have cx plus du. Fine. And then I'm going to take this x0, put it on the other side, like that. And now we're going to divide through by 1 over s. So this whole thing here, this is multiplied by 1 over s. And now I'm going to draw a picture, which is going to be a block diagram description of this set of equations here. And maybe you've also seen this picture before. So let's just draw it. So we're going to start with an input u. And then here we're going to have the matrix B. And then here I'm going to put a plus sign, and then I'm going to have a 1 over s. And then I'm going to have a matrix A. And then I'm going to have another input, and this is going to be x0. And sorry, I've got a bit of jumbled notation here. So the value of my state x at time t is equal to 0. This is equal to some vector of numbers x0. That's all I mean here. So this is x. This is just a constant if it's describing an initial condition. But it's like having a constant input here. And here we have c, and then we draw another path down here that goes through the matrix D, and then this comes and this gets summed here. And the claim is that so all of this A, B, C, D, U, X0, Y in this block diagram is encoding the same information as this pair of equations, but now everything's been put into our language of input-output systems, if you like. So this block here, it takes as input u, and it spits out some signal, which will be b times u. And so what's going on here, I'm going to call this x, and let's just try and work out what everything is saying here. So what's happening at this summing junction? This summing junction says that this signal here this is equal to ax plus x0 plus bu. Ax plus bu plus x0. So this summation here, this is all of the stuff on this side, and then multiplied by 1 over s, so this signal multiplied by 1 over s is equal to x. So this summing junction is encoding precisely this first equation. And similarly, this summing junction here is encoding precisely this second equation. So this is saying that y is equal to cx plus du. So here we have a block diagram representation of our state space model, which, remember, is basically just an alternative description for this ODE model, just a sort of a more standardized representation. And we've seen that we're able to describe the whole thing, including initial conditions, using our same input-output convolution framework. So there's kind of this slight cheat going on when you talk about convolution systems describing all linear time invariant systems, and you realize that you forgot to account for the effect of initial conditions, but just by making a small change we can bring initial conditions back in again. All of that said, you would normally still call the map from U to Y. That's normally what you would call the transfer function for this system. So when you kind of plot Nyquist diagrams and Bode plots and all of these things, you're typically focusing on the bit that's independent of initial conditions, but you can easily build initial conditions back into your analysis if you want. And so we're sort of probably going to be pressing ahead largely under the assumption that your initial conditions are 0. But here you can see how to modify all your pictures if you discover for your particular system of interest that the initial conditions are really critical to how it behaves, rather than just a sort of in many cases you want to sort of focus in on the effect of your actions on the system and how your actions can affect its behavior in the right way. And so you really want to focus in on the input U, and you don't want to get distracted by the initial conditions, which is, I guess, part of the motivation why you'd set those to be 0. But you can always bring them back in a completely consistent way within this framework if you want. So that's a bit of a long rant in the end about ODE systems and delays, but the point is just to sort of reinforce some of this input-output machinery and the use of Laplace transforms.